All right, so we're going to talk about linearization, which is really just tangent lines. And really, it's just a fancy way of saying, hey, we're going to use a tangent line to predict points around the point of tangency. Rather than dealing with a messy function, we can deal with a linear function, which is much easier for us to compute. So really, that's all this is. So if you ever are asked to find the linearization of something, really all you're going to do is find the tangent line to that thing. So again, just a reminder, to find a tangent line, I need three things. I need the slope, I need an x, I need a y. So find f prime at a, that's the slope. X equals a is your x value. Find f of x at that value, that gives you your y value. And then y minus f of a equals f prime times x minus a. That's the equation of your linearization. A lot of times they're going to want that in like L of x form, so we'll add the plus a to both sides to make it look like this, but it doesn't really matter. So we'll just start here. Find the linearization for y equals sine x at 0. Use it to approximate sine of 0.1. So if I want the linearization for sine x at 0, I need to find y prime, or dy dx, so the derivative of sine is cosine, and then y prime at 0 is going to be 1. And so there's my slope, and then x equals 0 is my x value, and then plug 0 in for x, and I get y equals sine 0, which is 0, and that's my y. So my tangent line is y minus y1 equals mx minus x1, and so I get y equals x. That's my linearization. Sine of x at 0 has a tangent line of y equals x. And if I graph it, that makes a whole lot of sense, because if I graph sine, looks kind of like this, and it looks like that. And then if I draw in my tangent line right here, it looks like that. Wow, that looks pretty good, right? So what I'm really doing is I'm going to zoom in on that spot. Now let's see if I can do that here. I wonder if it'll work. Oh, it works pretty good. Look at that. Y equals x right in here looks a lot like sine of x. So that means this gray line is a good approximation of the green line. So now I'm supposed to use that approximation. Zoom down here. So now I'm supposed to use that approximation to estimate sine of 0.1. So sine of 0.1 is approximately 0.1, because if I use y equals sine x and plug in 0.1, I get this. And if I use y equals x and plug in 0.1, I get that. So the sine of 0.1 is approximately 0.1. That's what that's showing me. Okay, well, I guess we can live with that. Let's see what else has happened. So find the linearization for y equals ln x plus 2 at x equals 3. Use it to approximate the ln of 2.9. Okay, fine. So if I want the linearization, I just want the tangent line. So if I just want the tangent line, I need y prime. The derivative of an ln is the derivative of the end over the end. And then y prime at 3 is going to be 1/5. And y of 3 is going to be ln 5. So y minus y1 equals m x minus x1. So then if I make my linearization as like a function, it's 1/5 x minus 3 plus ln 5. This right here is the linearization, okay? Now I'm going to use that linearization to approximate ln of 2.9. So I'm going to plug 2.9 into the tangent line. So ln 2.9 is approximately 1/5 of 2.9 minus 3 plus ln 5. So that's going to be 1/5 of negative 0.1 plus ln 5. So this is really going to be ln 5 minus, let's see, this is 1/5 times a 10th minus 1/50th. And you know what? I'm going to leave it just like that. And here's why. What we really want you to get out of this lesson is that what's happening here is if I start at one point, which is the point of tangency, and then I try to approximate something that's close to that point of tangency, what I'm really doing is I'm taking my slope, I'll do it right here, I'm taking the slope that's 1/5. And what that 1/5 represents is if I go from x equals 3 to x equals 4, I'd expect my y to increase by 1/5. Well, I'm not going from 3 to 4. I'm going from 3 back to 2.9, which means if I'm supposed to go up 1/5 every time I move up 1, I'm now going to only go up, well, in this case, go down 1/10 of that, because I'm only moving 1/10 instead of 1 whole unit in terms of x. If I rewrite that, this linearization says y equals m times delta x plus y1. In other words, if I want a new y value, I can do delta x times m plus the original y value. I take the slope, I multiply the fraction of it that I need, get my new delta y, add it to y1, and I have my new location. Even another way to write this would be y minus y1 equals m times delta x. In other words, delta y equals m times delta x. In other words, my change in y is my slope times my change in x. Because if I go up 2 units, then I need 2 slopes. If I go up 1/10 of a unit, I only need 1/10 of the slope as my estimated change. Okay. Draw a tangent line to the glow at -1, 1, whoa, went too far. There we go. Draw a tangent line at 1, -1, and at the relative min and max, pardon me. So here's 1, well, pardon me, -1. There's a tangent line. Here's 1. There's a tangent line. And at the relative max, there's a tangent line. When and why is a tangent line above the curve? When is it below the curve? Well, we've already talked about this. The second derivative. When f is concave up, the tangent is, all right, so when f is concave up, the tangent is below f. Therefore, the linearization is an under approximation. Then the tangent is above when f is concave down. Therefore, the linearization is an over approximation. So a linear approximation is an over approximation when f of x is concave down, and an under approximation when it's concave up. Okay. The last thing I wanted to do here is I wanted to pull up a calculator just so you could see just how close these linearizations are. So I'm come back here and look at 2 real fast. So I brought up the calculator and I'm going to graph ln x plus 2 near 3. So let's see, if I graph y equals ln x plus 2, and I'm going to zoom 6 it here, give me my regular window, and then I'm going to graph my tangent line, which was what? 1/5 x minus 3 plus ln 5. 1/5 x minus 3 plus ln 5 So there's my tangent line right at 3. And if I zoom in here near 3, you should see, wow, those are pretty close together. So I zoomed in right now with the screen. I can also zoom in with the calculator. Zoom in over here at 3. Come on. Come on. Wow, so slow. Okay. So there's, I think, x equals 3 about there. No, this would be x equals 3 right here. And I'm dealing with 2.9. I mean, they're right on top of each other. They're really, really close. So this linear approximation is great when I'm close to the curve like that. So one of the other things I want to talk about here is that we would never, for this example here, we would never say, find the approximate, find the tangent line at 3 and then estimate f of 5. No, 5 is way too far away. If we're going to use a linear approximation, we're going to usually look within like a half to either side, at most maybe 1 to either side. Beyond that, we're going to be too far away from the curves, and that linearization isn't going to be close enough. All right, so I am done. You guys need a bad joke, so here's your bad joke of the day. Why did Adele cross the road? Why did Adele cross the road? So she could sing,